In mathematics, a singularity is in general a point at which a given mathematical object is not defined, or a point of an exceptional set where it fails to be well behaved in some particular way, such as differentiability. See singularity theory for general discussion of the geometric theory, which only covers some aspects. For example, the function on the real line has a singularity at x equals 0, where it seems to explode to plus or minus infinity and is not defined. The function g equals x also has a singularity at x equals 0, since it is not differentiable there. Similarly, the graph defined by y2 equals x also has a singularity at this time because it has a corner at that point. The algebraic set defined by in the coordinate system has a singularity at because it does not admit a tangent there. Real analysis. In real analysis, singularities are either discontinuities or discontinuities of the derivative. There are four kinds of discontinuities. Type 1, which has two subtypes, and Type 2, which also can be divided into two subtypes, but normally is not. To describe these types, two limits are used. Suppose that is a function of a real argument, and for any value of its argument, say, then the left-handed limit and the right-handed limit are defined by, constrained by, and constrained by. The value is the value that the function tends towards as the value approaches from below, and the value is the value that the function tends towards as the value approaches from above, regardless of the actual value the function has at the point where. There are some functions for which these limits do not exist at all. For example, the function does not tend towards anything as approaches. The limits in this case are not infinite, but rather undefined. There is no value that settles in on. Borrowing from complex analysis, this is sometimes called an essential singularity. A point of continuity is a value for which, as one usually expects, all the values must be finite. A type 1 discontinuity occurs when both an exist in a finite, but one of three conditions also apply, does not exist for that value of, or does not match the value that the two limits tend towards. Two subtypes occur. A jump discontinuity occurs when, regardless of whether exists, and regardless of what value it might have if it does exist. A removable discontinuity occurs when, but either the value of does not match the limits, or the function does not exist at the point. A type 2 discontinuity occurs when either or does not exist. This has two subtypes, which are usually not considered separately. An infinite discontinuity is the special case when either the left-hand or right-hand limit does not exist specifically because it is infinite, and the other limit is either also infinite or is some well-defined finite number. An essential singularity is a term borrowed from complex analysis. This is the case when either one or the other limits or does not exist, but not because it is an infinite discontinuity. Essential singularities approach no limit, not even if legal answers are extended to include. In real analysis, a singularity or discontinuity is a property of a function alone. Any singularities that may exist in the derivative of a function are considered as belonging to the derivative, not to the original function. Coordinate singularities. A coordinate singularity occurs when an apparent singularity or discontinuity occurs in one coordinate frame, which can be removed by choosing a different frame. An example is the apparent singularity at the 90-degree latitude in spherical coordinates. An object moving due north on the surface of a sphere will suddenly experience an instantaneous change in longitude at the pole. This discontinuity, however, is only apparent. It is an artifact of the coordinate system chosen, which is singular at the poles. A different coordinate system would eliminate the apparent discontinuity, e.g., by replacing latitude, longitude with n vector. Complex analysis. In complex analysis there are four classes of singularities, described below. Suppose U is an open subset of the complex number C, and the point A is an element of U, and F is a complex differentiable function defined on some neighborhood around A, excluding the U, A, isolated singularities. Suppose the function f is not defined at A, although it does have values defined on U, A. The point A is a removable singularity of f if there exists a holomorphic function g defined on all of U such that f equals g for all z in U, A. The function g is a continuous replacement for the function f. The point A is a pole or non-essential singularity of f if there exists a holomorphic function g defined on U with g non-zero, and a natural number n such that f equals g, n for all z in U, A. The number n here is called the order of the pole. The derivative at a non-essential singularity itself has a non-essential singularity, with n increased by 1. The point A is an essential singularity of f if it is neither a removable singularity nor a pole. The point A is an essential singularity if and only if the Laurent series has infinitely many powers of negative degree. Branch points are generally the result of a multi-valued function, such as or being defined within a certain limited domain so that the function can be made single-valued within the domain. The cut is a line or curve excluded from the domain to introduce a technical separation between discontinuous values of the function. When the cut is genuinely required, the function will have distinctly different values on each side of the branch cut. The shape of the branch cut is a matter of choice, however, it must connect two different branch points which are fixed in place. Finite times singularity. A finite times singularity occurs when one input variable is time, and an output variable increases towards infinity at a finite time. These are important in kinematics and PDEs. Infinites do not occur physically, but the behavior near the singularity is often of interest. Mathematically, the simplest finite times singularities are power laws for various exponents, of which the simplest is hyperbolic growth, where the exponent is 1. More precisely, in order to get a singularity at positive time as time advances, one instead uses. An example would be the bouncing motion of an inelastic ball on a plane. If idealized motion is considered, in which the same fraction of kinetic energy is lost on each bounce, the frequency of bounces becomes infinite as the ball comes to rest in a finite time. Other examples of finite time singularities include the Paine-Levé paradox in various forms, and how the precession rate of a coin spun on a flat surface accelerates towards infinite, before abruptly stopping. Hypothetical examples include Heinz von Foerster's facetious Doomsday's equation, algebraic geometry and commutative algebra. In algebraic geometry, a singularity of an algebraic variety is a point of the variety where the tangent space may not be regularly defined. The simplest example of singularities occurs that cross themselves. But there are other types of singularities, like cusps. For example, the equation y2 minus x3 equals 0 defines a curve that has a cusp at the origin x equals y equals 0. One could define the x-axis as a tangent at this point, but this definition cannot be the same as the definition at other points. In fact, in this case, the x-axis is of double tangent for affine and projective varieties. The singularities are the points where the Jacobian matrix has a rank which is lower than at other points of the variety. An equivalent definition in terms of commutative algebra may be given, which extends to abstract varieties and schemes. A point is singular if the local ring at this point is not a regular local ring.